difficult to use this. Okay. So this is again invariance problems in invariance principle. Invariance principle. I should rather say just combinatorics problems of invariance principle, because invariance principle problems are present throughout in number theory, also in certainly in algebra. Lot of them are there, but we are focusing on the combinatorics or CS type questions in invariance principle. Okay, the combinatorics type questions, or at least they seem like that on the surface. So here is the first question which we didn't discuss last time. There are so there are A white. So again, this is about chips, but this is maybe a harder version of what we had done last time. We have some white chips, and we have some B black chips, and we have C red chips. Okay. Again, this is only one person is doing this thing, but what we are doing is we are choosing two chips. Okay, we are removing one. We are choosing two colors, removing one chip each of that color, but then we are adding two chips of the third color. Okay, so let me write that. As you can see, it's a little difficult to write in this, so just pardon me for that. For maybe a few more days, I have to choosing two colors, removing one chip each of that color, and then adding. So the number of chips, as you can see, is not changing. Adding two of the third color. Okay. Now the question is again, for what ABC is it possible to, make all the chips in the end of the same color? Okay. Yeah, so maybe I missed you. Yeah, it's possible. Yeah. So just check out the question once. Okay. The goal is to end up with. Last time we were doing a simpler version of this. So here you can, yeah. So sorry. Yeah. Now this time we are adding two of the third color, and the goal is for which ABC is it possible to get to a place where you have all chips of the same color. Okay. So for which triples, I should say, for which triples ABC is it mod 3? Okay. So that's maybe a good hint. Let me also think about it. Okay. We just see the whole question. Chips, to make all chips. Okay, I didn't think mod 3. That's interesting. Same color. So 1 second, let me just say the question. Just let me say the question again. Okay. So we have 3 colors and we have some number of chips of each color. In every move, we are going to choose 2 of the colors and we are going to reduce, we're going to delete 1 chip of the chosen colors. Okay. But then we are going to add 2 chips of the third color. So the number of chips is not changing. Okay. So this is slightly difficult in that sense. But then the goal is to know for what ABC is it possible to make all chips of the same color in the end. Okay, so basically we need to find some sort of an invariant. Chandan is saying something related to mod 3 is not changing. Let me see. Oh, okay. Okay, so I see that. So the hint is it's going a little fast because, okay, I think maybe I forgot to send this problem but to everyone, but still um, something, sorry, why? Handwriting, yes. Okay, okay, so much of that. Yes, so let me just send WhatsApp this to you, right? Okay. Yeah, so okay, I can just say it first. Yeah. So you see, as I said, right, we have three. Can others read it? So okay, anyways, we have A white chips, B black chips, and C red chips. And you want to choose two colors, okay? And you're going to decrease the chip num. You're going to just remove one chip each of the chosen colors, like I've done here. Okay. And then for the third color, you're going to add two chips. It is just like that, simple. Okay. And then the question is, for which three chips, for which starting positions of chips can you manage to get, make all chips of the same color? And so the other two, there'll be only one color with chips. Other two colors will not be there. Okay. Yeah, so as I said, I'm using this old computer, so it's a little difficult to write here. Yes, exactly. So something related with mod 3. That's right, yeah. So A minus B, even B minus C and C minus A mod 3 is, it's implied. Yeah, but let's write it. Yes, right. Does not change. Does everybody see this? So yes, so note that eventually we want something like, well, not something like, it's just A plus B plus C. In the end, we want this or similar cases. Adish, is this visible? Is this readable? Okay. Mod 3. Okay. Right. And so, I mean, yeah, it's very simple from here, right? Because you see, eventually, you just look at eventually what you want and what properties it has, right? So eventually we want this and no, wait. Yes, yes, right. Yes, right, exactly. B minus C would be 0 because, yeah. So eventually, if you suppose focus on this, then the first possibility, eventually you see the last two coordinates are 0. So the difference is 0 mod 3, which means that at each stage, the difference between the second and the third coordinates should have been 0 mod 3. Is this okay with everyone? Because see, whenever we are making this operation, okay, then the difference mod 3 is not changing. Okay, so if you had ABC and you're coming to A1, B1, C1, in any of there are three possible moves, right? At each, three possible choices at each step, right? Whatever move you're making, whatever A minus B was modulo 3, A1 minus B1 is also the same thing, modulo 3. And similarly for the others also. Okay, and that is not changing. I'm not saying it's 0 modulo 3, I'm just saying it's not changing. But eventually, you see two of this, if you are on this case, then this is 0 mod 3. So second and the third coordinates difference is 0 mod 3, which means that if you want to end up with this, then initially also you should have had that B minus C is 0 mod 3. Okay. So to reach here, you should have had that B minus C is congruent to 0 mod 3. Okay. Uh, we reduce A by 1, right? Uh, yes, it's not constant. It's not constant, but it is constant modulo 3. The difference is constant modulo 3, yes. So it becomes this if you choose A and B, the colors too. Now you look at the difference between this and this and A and B. They are same, exactly same. But these are also equal modulo 3. Because this is B minus C minus 3. Okay, you see, it doesn't change. It changes, it doesn't change modulo 3. That is the good thing. Yes, yes, exactly. That's the trick. Obviously, it's a little surprising, not difficult, little difficult, but we had done a similar question last time, so that maybe it's. But anyways, yeah, this is what will happen. Okay. You can check; it's the same thing. A minus B is not even changing, right? Right. Numerically, it is not changing because A minus B was A minus. It's not changing. No, no, we are not going there. No, that's a different question. That we will have to deal with later. Yeah. First, we will be able to know what are the possible places you can reach. And then, but to show that you can actually reach there, you have to use induction or something like that, or an algorithm. So if we are starting with A, comma B, comma C, and if we have to maybe after some finite number of steps, if we have to reach to this, then what can we say about the initial A, B, and C? Because finally the B minus C, by B and C, I mean the second and third coordinates. Because finally the second and the third coordinates, maybe that's the notation I should have used. First coordinate, second coordinate, third coordinate. Okay, but anyways, because eventually the difference between the second and the third coordinate is 0, modulo 3, 0, 0 only. So initially also it should have been 0, right? So this means that this implies that this B should have been same as C modulo 3. And because finally the first coordinate and second coordinate difference is same as the first coordinate, right? So, so what can we say about the initial? What does it imply about the initial things you start? Well, actually nothing, right? Initially, like just with this difference that this minus this, the first and the second coordinates of the final numbers is a plus b plus c mod 3. Okay. And the first and the third coordinates is also a plus b plus c mod 3. So what does it say about the initial numbers? Um, right. Yes. So let's write that. Just let's write that. So a plus b plus c minus 0, just that same thing as a plus b plus c, is congruent to a minus b mod 3. Okay. And similarly, a plus b plus c minus the third coordinate is same as a minus c mod 3. So what can we say from these two? Okay, yeah, let's just write all that. 2b plus c is congruent to, yeah. So maybe Chandan was just, right? Yes, yes, right. Um, yeah, whatever, yeah. And basically that's what Chandan is saying, that basically b and c are both congruent to 0 mod 3. Is that right? No, but that is not useful. That we already have. B minus a is congruent to 0 mod 3. Why? C minus, why? No, but in the end, it is not 0. Right? Sorry? Mm, okay. No, not 2 times. How do you get 2 times? Let's just solve this. Yeah. So no, let's get 3. So this is 0 modulo 3. But that's not useful. 3, no, 3 times and then it's not useful at all. Right? One minute. I don't get anything. Right. So the first and the second, first and the second is that. Yeah, so basically we cannot say anything then. Is that right? Or what can, no, no, yeah, that is the, apart from that, yeah, that we are able to say, but apart from that, we cannot say anything more. Okay, because even if you write it like this, 2b is congruent to minus c, then I mean, how does it help? Because minus 2, minus 1 is basically 2, right? Minus 1 is same as 2. and so that is B congruent to C. So we don't get anything more. So all we know is that two of them have to be the same modulo 3. Okay, any two. It's not just B and C actually. Any two of them have to be the same modulo 3. Mhm. Yeah, no. But that will be for a different. That is not necessary. But if you want to end up, yes, yeah, in those cases. So I mean, either one of it is fine. Okay, so two of them have to be the same modulo 3, but it could be any two. At least two of them, yeah, right. At least two of them should be the same uh, modulo 3. Okay, so let's just see if there is anything more. For now, we are just getting this. A minus. So where, what exactly? Mhm. Right. You mean the second equation? Okay. So why are you getting? No, this is right because you see the first. So I'm just doing the first coordinate minus the last coordinate, and so that's what I'm doing here also. First minus last. That's A minus C. Right. So that is fine. Yeah. Oh yes, yeah. So that you don't have to think of it explicitly. I suppose we can just use some sort of an induction, right? Okay, let's see. Let's see. So first, let me write the condition. Okay, two of them have to be the same modulo 3. Okay, at least that's a necessary condition. Okay, so necessary condition. Two colors. Yeah, maybe induction will not work. I'm sorry. We have to think. Have to be same modulo 3. So let's take an example. Okay, maybe let's take 1, 1, and 4. Oh, this will obviously work. Um, let's take uh, let's take 4, 7, and 6. Can we? Let's see if we can just make this work. Hmm. Hmm. Hmm, hmm, hmm. Huh. 5. No, that will become 6. You have to increase it by 2. So that will maybe not. Yeah, it always increases by 2, uh, or decreases by 1. Hmm. Well, maybe we have, yeah, maybe we have not. We have kind of used it in the process only, right? In the step, kind of we used it. Yeah, but let's try to explicitly get from here to whatever it is, 17, something like that. I want us to use a very clear strategy. Mhm. Right. Oh, no. Okay. No. So, but we are, yes, we are looking at this one basically. If you're looking at this one, I mean, it doesn't matter. So yeah, basically, see, it doesn't matter which two are the same modulo 3 because you can always, yeah. So right, right. The sixth, the one that is different modulo 3 will become 17. Yes, so first we should try to make, if we just do it like this, yes, so maybe we can do something like this, right? Just, yeah, 6, so we can increase the 4 by 2, and no, but then the becomes 5. No, that's fine, we get this. Is that right? I'm decreasing the 7 and the 4 because, we, yes, Raghav said that will, those will become 0 in the end, right? So I'm just making them equal. Now you can just continue simply. Or is it not correct? No, so I'm just decreasing the 6 to 5, and 7 is going to 6, and 4 is increasing to 6. Okay, is that right? So I'm doing +2 -1 -1. From here we can do it. Right. Okay. Because as you said, as Raghav said, that if you want to make the 6 13 or 17, but yeah. From here you can just do decrease these and increase this and just continue. But how do we prove that it can always be done? Two of them can be equalized. Now, I think this is the only condition that two of them have to be same modulo 3. One second. Last time we used induction. So if you assume, but you'll have to apply induction. So you apply induction. Yes. Okay. So if okay, so let's say that we are starting with a comma b comma c. Okay, and we can, so it's without loss of generality, right? We can assume that b and c are same modulo 3. Okay. So assume let's assume that b and c are what do you say? Uh, I mean, we can just assume that they are multiples of 3. No. Yeah, that's right. But you can increase and decrease, right? And you can make them both 0 modulo 3. Okay, so you're saying that. Okay, so assume that A is congruent to And we can make these assumptions because we can just swap it. It doesn't matter. No, yeah, that's right. But more than that, you can. No, wait. A and C, but that's a very strange thing. Let me assume that A and B are same. No, or let's just assume that B and C are same because that's what we kind of did here. So it's in this no, but what I am saying is you can actually assume that both are 3K. I mean 3K1 and 3K2. Because you see, you can, I mean, you can decrease it, right? You can decrease them or increase them to it, right? Mhm. Yes, yes. Yes, that's all. Yes, sorry, it's very simple. Yeah, as Rampal said, and so Raghav is saying, trying to say the same thing. I understand. Yeah, so B is bigger than C, and you can certainly by this operation you can make them equal. Okay, so if you assume this, we can assume, and actually, yeah. So what I'm saying here is, so you don't need that actually, but you can do it, but you don't need it. And we want to make them equal, and you can make them equal, right? It's very clear because just at each step, uh, already has been said, you do. No, no, but it should work, right? This one should make them equal because you're decreasing this B, right? And you're increasing the C. But they are equal modulo 3, they will remain equal modulo 3. So they have to become equal at some point. Just C. That is all almost, yeah. Uh-huh. 0. Okay. Okay, that also so. Yeah, so it's fine. It's simple. Yeah. Basically, the idea that we want to make them equal was the key. I think Adish and maybe yeah, people were thinking that only. So yes, so it's done. Good, right? Invariant. But life is not always so good. I mean, these are good problems. These are doable problems. That's why. But usually, finding invariance will be a first step towards, at least knowing what are the possibilities, narrowing down the possibilities. And but here in these are problems, simple problems, relatively. So yes, yes, exactly. That's why I did. That's why I didn't do this. Jump to these problems in the lab. These problems are not simple. I mean, uh, but anyway, it's a good ideas. And finding invariance is always important. Whether you are analyzing algorithms, you have to find a loop invariant. Something which will establish the truth, or you have to find a monovariant which will establish the ending of the algorithm. I mean, it's just everywhere. Okay, but we are kind of limiting ourselves to simple combinatorial. Um, but let me next problem. We have done a lot of. Let me do a little kind of problem which is also a good theorem. Okay, it will be a uh, good thing. Okay, so and let me just say application of invariance. It's a problem. It's a problem, but it also leads to a good theorem. Maybe we won't do the full generality of the theorem, but yeah, application of invariance. Just 1 second. I close the window. So these neighbors here, they always fight. Visions of invariance. Basically, if this is in graphs, Set it. So let's say that I have some the terminology. I have this. So you don't need graph theory for this. Okay, it's just a simple question. It will usually in an exam will be given without the language of graph theory. Given as some friends and people and a party and things like that, whatever. But this is how we work. So let's say that this is the situation, and I have to also label the vertices. And I will not be doing this completely. I'll be leaving a lot of things for you to check and try. This will be, you have to fill in a lot of things. See, I have 6 points. And you see, every point has every point has some neighbors. Okay. We are going to encode that information in a sequence. Very important sequence. Okay. That's what we're going to do. And that's called the graphic sequence of the graph, but doesn't matter. Okay. I'm going to make a sequence. I'm going to write it as a coordinates. So for one, how many neighbors are there? That's all. Okay. So it's like a simpler information than carrying the whole graph, but that much information itself can sometimes be very useful to prove things and to get obstructions to things and so on. Let's say I take the first vertex, okay, and I take one of its neighbors. I'm sorry, it has only one neighbor. So number of neighbors, it has only one neighbor, so I'll just write 1. The second vertex has 3 neighbors, 3 edges coming out of it, 3 lines coming out of it. That's what I mean by 3 neighbors, 3. So you can understand, right? Now the vertex 3 has 2 neighbors, and so on. 4 has 2 neighbors. Okay. So given this graph, I have this sequence. Okay. It's very easy. But now a very fundamental question is, given an arbitrary sequence, is it the sequence of some graph? You understand what I'm asking? Right? Is there a graph for which this is the neighborhood sequence or graphic sequence of that graph? Okay. Then that's the question. So maybe I'll give you some numbers now. Again, let's just transfer to 6 vertices for now. Let's say that I give you 2, 3. Can you make me a graph? Or you don't even have to make me a graph. You can tell, yeah. Is there a graph for which this is the graph sequence, for which the first vertex has 2 neighbors, second vertex has 3 neighbors, third vertex has 3 neighbors? I have discussed these things in graph theory class earlier, but in invariance, it is a very fundamental question. And we'll see a good technique to solve it. Yeah. So is there a graph? Is there a graph? It's framing it like this. Is there a graph for which one has 2 neighbors, right? 2 has, you see, 3 neighbors. Got that. Yes, we have done. I think you were there. Yes. Okay. Mm-hmm. Yes, the sum of all these things should be even. Does everybody agree with that? Yeah, I mean, Adish, do you agree with that? If you have not done graphs, sum of the coordinates, total number of relationships, you could say. Yeah, sum of the coordinates has to be even. See, this is a necessary condition. If this has to be the graphic sequence of some graph, the sum has to be even. So, would anybody want to explain that? Yes, it's going to be twice the number of edges. Yeah, Adish? Yeah, it's going to be twice the number of edges, right? Because every edge is essentially getting every point need not have a neighbor. Yes, yes, but here it is not zero. But the point is that, I mean, every time you have, if there was a graph, then in that graph, this edge, if there was this edge in that graph, in our graph, which we want to make out of this sequence, then this edge is getting counted twice, right? It's getting counted in the neighbor of 2 and is getting counted as a neighbor of 3. I mean, yeah, it's while counting neighbors, it's going to getting counted twice. So obviously, the sum has to be even. So that's fine. But this is, I mean, that is not enough, right? I mean, that doesn't seem to be enough all the time. It is certainly not. So then how can we answer this question affirmatively? I mean, one way is you can make the graph, but you cannot always make it directly so easily. Mhm, mhm. You mean the vertices you're partitioning? Okay. Mhm, 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 mhm. Um, yeah, yes, yes, yeah. So I think there is something like that. It is, if I'm not wrong, it is called some Ardos-Galai theorem. But that's some very complicated theorem, I suppose. But it's not this only. But it has to do something with taking subsets of the graph and then taking some. Okay. It is, yeah. There is a theorem like that. It is called Ardos-Galai. But that is a very complicated one. That's not useful. To actually, that just gives a condition. It's useful improving things, but we want to like recursively, like a CS type way, know if this is a graphic sequence. Okay. So it's because I want to take it in a certain direction. Let me, if I told you, if if 1, 2, and you can see how the sequence is related. Uh, if Okay. So the fourth vertex has degree 1. So let's say 3 is the neighbor. You can make that 10. Not necessarily, because no, these two are not adjacent, right? They are just adjacently numbered. You're right. Okay, so you've actually given an answer. Okay, that's fine. So that's okay. Yeah. That's good. You've made it. But that's a little ad hoc, I could say. Let's say that if I told you that if 2, 2, 1, 2, 1, if this one 5 vertices, yes. Okay, I'm doing because we want a recursive answer, and we are going to use an invariance to prove that this the converse. Let's see. If this if this is a graphic sequence, let's say if I told you this, then can you from here, I mean, I can just immediately replace these numbers by arbitrary things. Okay, then we cannot take examples and check, right? But, okay, so forget, you can assume these are just variables. If this is a graphic sequence, then does it imply that that is a graphic sequence? Yeah, so both of you guys are, I think, saying the same thing, add nodes. That's what we have to do. Okay, so mhm, mhm, yes. Mhm, 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 mhm. That would also happen, yeah. Yes, yeah, but that's again a special case. Yes, so that's the point. So you want to go to a simpler graph, but keep the same sequence. Yes, yes. I understand. I'm not trying to drop. That is another point, but I'm just building on your point. You are saying that you want to keep the exact same sequence, but yet go to a more convenient graph. Uh, No, no. That's okay. No, but this is a different point that we are making here. Is you do an operation which leaves the graphic sequence invariant, but takes you to a more convenient graph. Okay, that will be the idea eventually, I think. Okay, that is basically what we are going to do in here. Okay, but yeah, that's what we'll do. But do not think that you could make the graph into two disconnected pieces. Okay, that you cannot do, because if I gave you that each of these had 4 neighbors, then there cannot be any disconnected graph in which with 6 vertices and everybody has 4 neighbors. Yes. No, but you see, but then how will that help you to answer if this is a graphic sequence or not? No, no. So see, no, but in this way, you may not be able to. But you are not changing the degree of any vertex, right? No, no. 1 minute, 1 minute. So, Sampath, are you changing the degree? Okay. Okay, but that is. But then, what will that function be? Simple. Yeah, I don't know. Okay. What we are going to do is not. It is not going to even change the degree sequence and take us to a simpler graph. But what you are saying is, yeah, the answer will not change. So that's a much more bigger possibility, but I don't know. Yeah, it's very vague at this moment. One has to think about. Okay, maybe if I look into that Erdos theorem, there's something like that. Then I don't remember the proof and so on. I mean, in the sense that I don't even know the idea now. Okay. Anyways, but let's see this one because this is where we want to discover the invariance for this. But there are so many other questions. No, no, not necessarily remove the leak. So that is certainly a possibility. But what I have in mind is yes, this is the answer to this particular question that I asked is yes. And let me answer it through, I mean, as people can already see, I suppose, in the sense that you have to basically, so what we are doing is we have these 6 vertices, right? Then what I'm basically doing is I'm doing A2 minus 1, right? A3 minus 1 maybe. Till where? I'm doing till A1, right? And then I am, so that's, let me write that out clearly. You see, so I'm giving you the simpler sequence, but I'm removing the neighbors in some sense, but it's not exactly the neighbors. Okay. What I'm doing is I'm doing A2 minus 1, A3 minus 1. Till when am I doing this? Till A1 minus 1. Right? I'm, yeah, the next A1 terms from each of the, from the next A1 terms, I'm removing 1 from each of them. Okay. And then this is A1 plus 1, I mean, A1 plus 1 is 1 and A6. Or just maybe you can write AN. So if I told you that this bottom one is a graphic sequence, then the top one is also a graphic sequence, right? Because all I've done, you can understand, right? If there is a graph for this, let's say there is some graph for this on n minus 1 vertices, then how do you make graph for the above one? You just add a new vertex, right? 1, and you make so from 2 to A1, right? From the vertices 2 to vertex number A1, dot till A1, you make these neighbors of 1, right? Then you see the vertex 1 will have A1 neighbors, which is what we want, and the neighbors of each of these have increased. This part doesn't require an invariant. This is like a simple thing. The converse will need invariants. Yes, yes. Okay. Uh-huh. Yes. Yeah, let's take an example. Yeah, let's take an example. So uh, no, they are not connected. That's what. So, but we'll see. So what I'm saying is they're not connected. But we can make a graph in which they are connected. There can be several graphs. I'm just making one of them. So I want to know if this is a graphic sequence, but then if I told you that this one, you see, one is decreased from the first 4, or rather the 4, the first 5, from second to fourth, fifth position, one is decreased. If there was a graph for this bottom one, then I can make a graph for the top one also, right? Oh, no, no, no. Yeah, certainly. No, that I'm coming to. That is, I agree. But sufficient conditions have to come from necessary conditions usually, right? First, you know what is necessary, and then you see which of the necessary ones you combine to make a sufficient condition. But we cannot magically arrive to sufficient conditions, usually, right? So, I mean, this is the easier. That's right. That's right. This doesn't imply anything in that sense. But let's see. Yeah. Okay, not anything, but my point is, yeah, if I told you that there was a graph for this sequence, then you can just take the vertex 1, and you want 4 neighbors, and you can just add it to from 2 to 4. There may be other graphs, but this will work. So 1, 2, no, 2, 3, 4, and also to 5 I have to. Is this point clear to everyone? First question. Then we'll come to the. I'm taking a simpler graph. I don't even know if the bigger one has a graph for it, but I'm just imagining, let's say there was, and let's take a simpler graph, right? But then, if this simpler graph, no, 1 minute. Now, this is one of the very strange theorems, okay? But anyways, the point is that I'm taking the simpler graph, right? And if the simpler graph has the sequence, then I can make a sequence for the uh, for my original sequence. I can make a graph for my original sequence. Okay. So the answer to this is yes. No, yeah, you can certainly continue, right? In the sense that, so this is actually a very strange theorem in the sense that we are getting a sufficient condition. Do you guys see that, right? If this is, so this having a graph is sufficient to imply that this has a graph. Okay. Okay. It's a, I mean, okay, but necessarily sufficient in this language game, you could say it's necessary for the, or not implementation, but anyways. But you see, what I'm trying to say is, how will this help you? This will help you to prove that something does not have a sequence. Sorry, something does not have a graph, right? Yeah. If there was, so if there is a sequence, no, sorry. If there was a sequence for this, then if there was a graph for the simpler sequence, then there is a graph for this above sequence. So this will help you to prove that some sequence has a graph, right? Because what you can do is, you can take this, you can simplify this like this, but you can again simplify this, simplify. Yes. That is fine, right? You can do that, yeah. But you can simplify these things, and you can just arrange these in non-decreasing order and so on. Okay. Non. No, that will not help us. No, that will not help us. No, if you could make a graph, then it will help you. No, yes. It doesn't mean. Yeah, that's right. This itself doesn't imply, but it does imply. But that has to be proved. It's not even believable at the beginning. Right? Yes. This itself doesn't imply. That's what I'm trying to say. That this will help you to show something has a graph for it. Some sequence has a graph. Okay. So you idea is you simplify till you reach a point where you can make a graph by hand, and then you can say that my original sequence will also have a graph. You can actually make it. Okay. That's fine. But as again, Sampath has been saying that this is not like good enough, okay, because the converse is not true. Maybe it gives you an algorithm to return yes, but not to return no. I mean, if yeah, if there is an answer in the sense that if it returns yes, then there is an answer graph for it. But if it doesn't return yes, that doesn't mean that there is no graph. Okay, it's that kind of thing. But the converse is also true. That is the thing. That is what we want to show. So what we want to show is, let me write down, and that is really where this comes. So this is a graphic sequence. Now I'm just using the word graphic sequence. If and only if this is a graphic sequence. That is graph sequence. So we want to say that if the first one is a graph sequence, then the second one is a graph sequence. That's what we want to show. The other one we have shown already. So basically, we want to show that if the smaller one doesn't have a graph for it, then the bigger one also doesn't. Imagine that's the beauty. That's the good thing about this. So yeah. So how do we show this? That if the above one has a graph for it, then the below one also has a graph for it. How did we go from the below to the above? Right? If we had a graph for the below one, then we just took another vertex and we just made the first whatever number of neighbors we needed. We made them the neighbors of the new one. We were done. How do we do this one? And just before you guys, you can assume that this is sort of like this. You can assume that this is not a problem. We can permute. Doesn't matter. The graph doesn't change. Just relabeling the. If the above one had a graph for it, how do you show that the below one also has a graph? Just think. I just Google this Parados thing. Maybe it's in the book very clearly. So maybe see it there. Yeah, it's in Douglas West. It's very clearly given, but it's means the one that Sampal was saying related to that. I don't know if it's. No, but you see, no, but here you see, you're just given that this has a graph. You cannot decide the graph. I mean, I cannot decide the graph, right? No. Permuting is no. I'm just renaming the vertices. That is nothing. Right. See, that is. Uh, I don't know exactly. I don't know. That's why it's a question that this. Yes, yes, but that's non-trivial part. Yes, yes, yes. There is, yeah. So actually, that is actually the idea, that there is a graph. So that's actually the part. That's the way to say that this. So see, we are saying that there is a graph for this sequence, but that is not very helpful. Just this, right? There is a graph for this sequence, but we want a graph for the sequence in which 1 and 2 are neighbors, 1 and 3 are neighbors, and 1 till the A1 plus 1th guy is a neighbor of 1. We want that kind of graph. If you had that kind of graph, then you were done. Yes. Okay. Okay. Yeah. Sure. No problem. Okay. So is it that's the kind of graph we are looking for? If we had that graph, then you could just subtract, right? Then it's fine. Right? I mean, if 1 and 2 were neighbors, 1 and 3 were neighbors, then you could just subtract 1 from each and you were done. So you need that kind of graph. Okay. Okay. But and I'll also leave here. Now you guys have to make that kind of graph using invariance. Okay. We need that graph. I mean, we want that graph such that 1 and 2, 1 and 3 till 1 and A1 plus, not like A1 plus 1, but A1 plus 1. You can just take a number, but the point is till, because it has A1 neighbors. So the next A1 people, okay, are our edges. You need that graph. By invariance, you have to make that graph. Okay. So I mean, you will assume something like, 1 has a neighbor with something other than that. Then you have to break off that neighbor and make a neighbor with something among these, and then somehow you have to make an adjustment. Just the core idea is this. Let's say that this 1, and let's say that this is the 2. You want 1 and 2 to be neighbors, okay? And let's say they are not. Well, but 1 has A1 neighbors. Let's say that 1 is not a neighbor with 2, but then it means that 1 has a neighbor outside these first A1 things. So let's say 1 has a neighbor with n. Okay. Let's say that 1 has a neighbor with n. So this is the line, and we don't want this line. We hate this line, right? We want 1 and 2 to be neighbors. Okay, so we have a graph, but the graph is not perfect for us. 1 and n are neighbors, 1 and 2 are not neighbors. So what would you do? I mean, you could say, no, I will just make this graph where 1 and 2 are neighbors, and I'll remove 1 and 1. You can say that. Right? Obviously, it leads to problems, and certainly. You can say, I'll do this because this is what I want. But then where is the problem coming? Well, the problem is coming that now you're increasing the degree of 2 and you're decreasing the degree of n, which you're not allowed to do. Is that right? Because I mean, you want to, otherwise, how will you want the same sequence so that you can subtract 1. But then you have to figure out a fourth vertex. You have to figure out a fourth vertex for which 2 was a neighbor of that, and this was not a neighbor. N was not a neighbor of that, and 2 was a neighbor. You have to figure out that vertex will exist because this is a decreasing sequence. 2 has more neighbors than n has. So there will be some neighbor in which 2 has, but n doesn't have. Yeah, and then you have to use that to make a switch. This is the idea. You have to build a proof out of this. Okay. I'll leave it here for today. Just think about this idea. I had done this topic earlier once, but that's not the point. It's a very interesting, very important here. because it leads to many more. This particular operation that we're doing is called a switch equivalence. It's a very important operation. In invariance in graph, this is like a pakka is a very ubiquitous invariant, that concept. Yeah, so today we went more theoretical than I planned to. Okay, but yeah. And Chandan, this other problem which you have asked me about, so there is a grade in which there are 16 numbers, right? That's also very theoretical. Okay. So I will not discuss that now. Otherwise, we'll have means next class also, because that will again go into some theory. Okay, that is necessarily theoretical. Okay, I feel, but either ways. Okay. Next week, so next week we will again go back to matrices, or no, we'll go to analysis. Okay. So next week we'll have 2-3 classes on again integration type of things. Okay, we'll do integration. Maybe one will be problem solving, 1.5 problem solving, and 1.5 will be like. Okay. And, but just think about this, and whatever you've tried, you can tell me. Okay. We can. Thank you. Yeah, I'm just trying to take more classes.